Okay, so in the next set of slides, I will talk to you about how directly you can use digital signatures or to be more precise, public and private key cryptography in order to create a cipher, in order to send messages securely and encryptedly, and how to consign a document digitally using a public and private key cryptography. Now, I should warn you that this is a very mathy part of the course. It's probably something that is more abstract than what you're normally used to, because we have to use a few tools from number theory in order to understand this better. So now this algorithm that I'm going to talk about is the RSA algorithm, which has been developed by three MIT professors. It's the Rivest, Shamir, and Alderman algorithm. Some interesting side effects here. This was an encryption algorithm which the US government actually wanted to prevent everybody from knowing, but the NSA, so the National Security Agency, pushed very hard for this to actually be public knowledge, just so that actually they can also use it and people can use it to securely send messages. So now, as I said, this will be a little bit mathematical. I'm trying to do it as much by example as possible so that you can understand where this is all coming from. So first we have to start with some background math, and that goes back to prime numbers. Now, prime numbers, as you know, is a number that is divisible only by itself and by 1, so it has no other factors, so to speak. Now, with that, we also use a expression which is that one number can be prime to another number. And what that means is that the greatest common divisor is 1. So an example is 4 and 3. 4 is not a prime number, but 3 is. But the greatest common divisor of the two of them is 1. So the two are prime relative to one another. So now there's some other examples. As you know, you can take any number that is not a prime number and describe it as the product of prime numbers. So one example here is 72, which is 2 to the power 3 multiplied with 3 to the power 2. Another one is 175, which is 5 to the power 2 times 7 to the power 1. You can see the factors, the prime factors that both of them use are different, right? 72 has 2 and 3, and 175 has 5 and 7. So those two numbers are prime to one another. Okay, now with that, there is a function which is useful. It's Euler's phi function. And what that number indicates is the number of natural numbers that are prime relative to a number n. Now this seems a little cryptic. Let me, say this. So, for instance, sorry, my slides are a little messed up here. Let's take an example here for some numbers, right? So take the number 5. Which numbers are prime to n, to 5? Well, it is the number 1. It's the number 2, right? It's the number 3 and the number 4. So all of those are prime to 5. Now let's take the number 10. What is prime to 10? If you take 9, well, 9 and 10 have the greatest common divisor is 1. 8, the greatest common divisor is 2 of the two, so that is not prime. So 8 is not prime to 10. 7 is. 6 is not, because the divisor is 2. 5 is not, because the divisor is 5. 4 is not, but 3 is, and 1 is. Okay, so therefore the phi function for 10 is 4. Now there's some useful properties of this function. So if you have a number which is a prime number, then the phi function for that number is n minus 1. Makes sense, of course, because all the numbers that are smaller than the prime number are all prime relative to that number, right? That's by definition of it being a prime number. Also, there's some useful features is if you take the product of two prime numbers, then that is the same thing as the phi function multiplied with one another, which is the same thing as n minus 1 times m minus 1 is n, and m are both prime numbers. So in the case, for instance, of our examples there of 70, what did we have here in the last set of slides? If you take, for instance, 2 and 3, right? So 2 is prime to 3, and both of these are prime numbers. So if you take 2 times 3 is 6. The number that they are, so the phi function for 2 times of 6 would be 1 times 2 is 2.